Hello, my name is Bryan Jenks, and I am a research analyst with the California state government. I run a YouTube channel all about programming, tech, productivity, academia, workflow, a little bit of lifestyle, basically all things tech, modern, and code. You can find me on YouTube with my name, Bryan with a Y, Jenks, Bryan Jenks, and today we're going to talk a little bit about R. R is a specialized language that deals with statistics and data science, and it's heavily used in academia and those in the data science field. I use it both personally and professionally. I have a couple of open source repos that use R, and we're going to talk a little bit more about it, its history, how to use it, and get you up and running with how to actually start using the language, import a file, make some charts and some graphs and plots, and do a little bit of analysis with that. And we'll cover the basics of what the language is, how it works, and let's get into it. So programming in R. R can be used for a lot of different things. It's widely used in data science, it's used in statistical research. You can create a variety of different types of documents and reports or any sort of analysis with R and its various packages and useful utilities. You can also create dashboards with various packages or the Shiny package, and it's widely used in academia for research and theses. R is an incredibly popular language. On the TIOBE index in this most recent year, it went from the 20th spot all the way up to the 8th spot, and it was one of the fastest growing languages this last year. So how is R so popular? Well, given that it's also a very specialized language for statistics, analysis, data science, academia, the fact that it's so highly rated is a testament to how popular and great of a language it is. It does have a lot of quirks. There's a lot of weird history and just things that have been left around in the language because of how old and strange it is. But it is a specially geared language for the aforementioned purposes, and it's so widely used and popular that's just a testament to how great it is. It does have a monopoly on academia. A lot of the fields of academia use primarily R for their analysis, their statistical analysis, and for use in theses, documents, publications, and it is widely used in the field of data science. Python is definitely one of the go-to languages for data science, and it is also used in academia. But R definitely does have its place. It is a specialized language that works in a lot of these areas, whereas Python is a more general purpose language. R was created in 1993, but it is an implementation of the S language, which was made at Bell Labs in 1976. So R is a mature language. It is conservatively maintained. The base package of R, not the packages that you can actually import, but R itself, the language, is very rarely changed. And when it is, it's usually with the utmost backward compatibility in mind. So changes to R rarely will break, and you can write base R code, and 20 years later, it will usually still run exactly how it ran before. It is highly extensible with its package system. There are an incalculable number of packages. More are being made every single day. Even I've made a package at this point. And R is a vectorized language, which means that even single values are just vectors of size 1. And this makes it so that there are a lot of power that you can get out of these vectors, and it's easy to perform analysis and bulk operations. If you've ever done JavaScript, it's kind of like using the map functions and putting an operation off of a whole array of values with one operation with minimal code. And we'll get more into that later in the course. R is also really interesting because it does have elements of both object-oriented and functional programming. And you can kind of do a lot, if not almost anything, with R. It's not a general purpose language. It is specially geared, but with pretty much most of these languages nowadays, you can do just about anything. The question is really, should you? And if there's a better tool for that job. I mean, you're not going to use a wrench as a hammer, but I mean, you could, but it's not necessarily what it's made best for. R is also great as an interface or an intermediary language between other languages. If you've ever done anything with R, or if you have worked with RStudio, the IDE for R, There is a lot of other languages that go into R development and that it works closely with for either reproducible analyses, creating good documents, or just improving speed, or the fact that R is single-threaded so that it needs an extra boost for its calculation speed. So R interfaces very well with C, C++. It works with LaTeX and Markdown. It is very closely put in hand with Pandoc so that you can create really great documents. JavaScript libraries come into play when you export to HTML documents. It's just a place that really connects well to other programming languages to produce really beautiful documents, reproducible analysis, and statistical interpretation of data. It is an incredibly strange but worthwhile language to learn if you do anything that touches data. You don't need to be a PhD or an expert in statistics to use this language and receive some value or benefit from it. When I first started with R, the first thing I did was just start writing really cool documents using RStudio and a little bit of R code. So you don't need to be an expert or use this as an expert to get a lot of value out of it. Now, it is worth mentioning that R and Python are kind of put up against each other in competition, especially in the field of data science, and there are pros and cons to both languages. I've used Python a little bit, I've used R a lot, but when it comes down to right tool for the right job, when it comes to reproducible analysis, the tooling, the graphics, the just ease of writing code that is legible and reproducible, I do personally prefer R. But there are pros and cons to both sides of the argument. R is a single-threaded language. This means that it runs slower, or if you've done JavaScript, it's just like the event loop, where you can only have one thing running at one time and you can't have multiple calculations occurring simultaneously. There are people who are trying to work around this and make changes or certain packages that can try and take advantage of multi-threading, but for the most part, R is single-threaded, so it can be somewhat slow. But there are workarounds and things around that. Python lacks R's robust ecosystem for stats libraries. There's just no other language, to my knowledge, that really has the amount of packages, tooling, and code built around statistics, statistical analysis, and all of that R has. R has an amazing wealth of code that's already been written and that has been widely used for decades. And R's graphics are infamously better than Python. R's graphics using the ggplot2 package are used in publications like the New York Times. I think the Chicago Tribune uses it. A lot of the infographics and visualizations you see in modern journalism or scientific literature are all done usually with R. Now, one thing where Python does have a leg up on R is the fact that it is a general purpose programming language, which means sure, you're going to use Python for data analysis, but you could also use it to write a web application. You could also use it to write a command line application. Again, you can do a lot of the same things with R, but Python is geared towards a more general purpose. You can do a lot of different things with it, and learning Python for data science would also be something that you could tie into learning Python for whatever, any other purpose. As long as the data structures that you use, the same sort of logic is implemented, you could use Python to build whatever you want. Whereas R is geared more for specific purposes. So that's all I have to do for this intro. So let's get into the language itself. All right, everyone. So to get started with R, the first thing we have to do is install R. If you go and search for R project online or just go to the website r-project.org, when you come here, the first thing you're going to see is this landing page. We want to go to download R. And it's going to ask you where you want to download from or whatever mirror it is. You're just going to pick a place that is close to you. I'm in the US and I'm in California, so the closest place to me, let's do Oregon State University. Honestly, it's not a big download. It shouldn't take too long depending on your internet. This computer I have is running Windows, so I'm going to download R for Windows. And then I'm downloading it for the first time, so I'm going to do base right here and just install R for the first time. And you get this nice big download button. Click that, and then it begins to download. Once your download is complete, we're going to open it up as it is an executable. And it's going to ask you to install. We want you to say yes. And once the installation is finished, you now have R installed. You have the REPL or the read eval print loop available, so you can actually just go to your command line, type R, do some command line R. I never do this. Typically what I do is I use an IDE, and the IDE I choose to use is RStudio, an IDE specifically designed to do R development and analysis. Now, you do have to have R installed before you put this on, but we just did that, so now we're going to install RStudio. And you can get to this by going to rstudio.com, and then we're going to go to this button up here, download in the banner. We're going to use the free version because this is open source software, so you can find the RStudio on GitHub, so it is free. I'm going to click download, and here it is for Windows. So I'm going to click Windows, and then that will download. So once that installation is finished, we're going to run that executable for RStudio. Now that it's finished, we are ready to go. So now I'm going to open up RStudio. We don't need to open R. You can just open RStudio, the IDE, and it will already be connected with R, and everything will work exactly as you would hope to expect. And this is what you'll see once you first open it. You can customize this IDE. You can do a lot of different things with it. We're not going to go into the IDE itself too closely. We're just going to mostly focus on the language, but this is my IDE of choice, and I've been writing R code for a few years, and this is what I would recommend using. It is specifically geared for R, though you can do different IDEs. You can do VS Code, you can do Vim, you can do Emacs. There are other R-built IDEs, but this is the one I choose and that I've been using since day one. All right, so the first order of business. How do you make a file and how do you execute it? It's the whole point, is that we're trying to write code and then actually execute that code and achieve a result. So right before we do that, I need to actually change this theme to a dark theme because I cannot stand light themes. Let's do something like Dracula. That's cool. So how to make a file. In RStudio, there's this little button right here, make a new file. You'll get a lot of different things, and over time you'll learn what each of these do. The most important ones that I'm going to focus on are R scripts and R Markdown documents. So first thing we're going to do is just start off with an R script. An R script is just a script file. It's just like when you write a Python file or when you just have a single file with code that you execute and then it runs everything inside of it. An R Markdown document is completely different. An R script is just something that you want to run the entire document in one go. So the first thing we're going to do is type print, and in double quotes, we're going to do hello world, the typical program. So now we're ready to execute this. I could save it. It actually might ask me to save if I run this, but here are your buttons to run. We can run this document, and we can rerun different code regions. Some of this stuff is for R Markdown, but we're going to just click run, or you can see it also gives you the hotkeys, Control Enter. I'm just going to click the button. If I run that down here in the console, you can see the action has been executed. Great. We don't even have to save the file for this to happen. So this file doesn't even exist on my file system yet. It's just all in RStudio. I haven't even made it yet. So to do this, we're going to just click the floppy, save that to the desktop, call it R script, and now we have a file. So where R scripts we can execute in a single batch, have all of the code in here and have it run right when we execute it or whenever we source the document, an R Markdown document is something different entirely. So we can create a new file and say, give me a new R Markdown file. So I actually had to update my packages in the system before I could run and create a new R Markdown document. But after I do that, this is what I'm left with. So the R Markdown documents can export to a variety of different formats. The universal format that we have is HTML because everyone's going to have a web browser. If you need to do PDF, you'll need to install a LaTeX distribution. I'm not really going to get into that. And if you have MS Word, you can also export to that format. But we're just going to leave it on the default of HTML. And I'm going to name this R Markdown. And the author is me. All right. It'll create a template document with a little bit of stuff in it already just to show you what it looks like once we create it. And I'll just run this just so you can see what the output would look like. This is an R Markdown document, so it's a Markdown document with a little bit of YAML in the header for some like meta options and settings. And then we also have these code chunks that are written in sort of similar pandoc format with the 3 backticks, but then in curly braces we also have different other options like what language and then options for this specific code chunk. So let's run this and see what the output is. I'm going to save it as R Markdown on my desktop. It will then run, and it goes through pandoc, knits it all together, and then the output will look like this. So this would what you would see in the browser. You have your code chunks, you have some output, and this is how the R Markdown documents work. But one thing you can do with R Markdown documents is you can actually write up text with your analysis or whatever code you're writing, and it doesn't even have to be R code. There are dozens of supported languages that you can use in R Markdown documents. So each of these code chunks, you could put SQL code, Python code, R, Stan, Julia, whatever. There's even JavaScript. You can actually put JavaScript in here because this is exporting to HTML. You can actually write JavaScript to affect the HTML elements in the document as you're exporting it through pandoc. So needless to say, I have a whole playlist on R Markdown documents and the crazy things you can do with them. But what we care about most is creating an output and actually executing some R code. So you could actually write up your analysis, you have a code chunk here, but you don't want to have to knit your document every single time when you're trying to look at some output. Sometimes you just want to quickly iterate, see some results, see a value, and you don't want to have to knit the document and wait for it to run through pandoc every single time, especially if it's a large file dealing with large data. Sometimes you just want to have little tiny results so you can move at an incremental pace. And this is one of the reasons why R Markdown and R are some of the greatest things for data science, just like Jupyter and Python, because it allows that quick iteration. So I could easily just click this little play button over here on this code chunk. You can see the banded rows. If I click on the play button, it'll actually execute this code chunk after the setup chunk. And so it'll run this because it sets up the system, and then it's going to run the second chunk, and it actually gives me the output right here. I don't have to knit the document. It's only executing the essential setup and then this code chunk. And now I can see the output, and I can adjust for this, and I can do whatever sort of analysis I want. Print hello code chunk. Cool, I can run this again, and now we have additional output. And this is how we're going to be working. You can do R scripts and have it run the entire code all in one batch, but typically my workflow that I use, and you can make this however you want it to be, is that I will use R scripts, source it all in one go, just to get clean and export my data sets or my data frames, if you're familiar with Python, pandas, and data frames. So I will just use a single script to just do all my actions to just give me a cleaned set of data ready to then put into an R Markdown report, analysis, document, dashboard, etc. So a little bit more of what you can expect from this IDE as well as the code is we have several panes here. We have our files that we can access in here if we have multiple scripts or documents. If we make a plot, it can open up in the viewer here if we were just going to make this in like an R script. We have packages that are installed. There's help if you actually run for help documentation, and another viewer if we were going to like run those HTML exports and put them in the viewer instead of a pop-out window. We also have the environment up here. This is where if we actually have a variable assigned a value, they will both appear up here so we can see which things are actually allocated already. We have history. I never really look at this too much. Connections if you have connection to a database, and tutorial if you want to take a tutorial in RStudio. So the first thing we're going to start off with is some basic syntax and some hotkeys. I live and die by the hotkeys I learn for every program. So as I go through this, I'm just going to teach you the hotkeys as I use them, because I just use them as I use the programs and write code. So first, and one of the most important things is how do you comment out items in your code. With this, it's going to be Control-Shift-C, and it doesn't matter if you're in a code chunk or if you're outside, it'll comment out with whatever syntax it actually uses for whatever area you're in. It'll actually use that syntax to comment out your code or your document. So in this markdown space, where it's actually a markdown document, if I do Control-Shift-C, it'll actually do an HTML comment, because markdown is basically an HTML document but with simpler syntax. So I also want to do that in my code chunks. So in R code, the hash symbol hashtag #, that is actually the same style of comment as Python. So if I can do the same thing, Control-Shift-C, I can toggle comments. This is really useful. You have multiple lines. It'll comment out multiple lines. Now it is important to note that R does not have a multi-line comment. So if you have something like a doc string in Python or anything that spans multiple lines, or like SQL comments or C comments where you have this style syntax, or even JavaScript, this doesn't really work for R. So what we're going to do is we are going to actually assign some values to some variables, one of the most important things in programming. So I'm going to assign this string to the variable myString. So now I can run this line of code, specifically just this line, by doing Control-Enter. You can see that little green popped up here. That actually means that I actually ran this line. Control-Space. Now with that variable assigned that string, you can see it has now appeared in our environment pane. The value myString has the value comment me with Control-Shift-C assigned to it. So now I can just print the variable, running with Control-Enter, and it will actually display in the code chunk below. If I wanted to run the whole thing, I could. So next, let's just use R as a basic calculator. You could do this either in the console, or you could just do it in the code chunk executing the line with Control-Enter. If I run 7, it just displays 7. If I did 7 plus 7 and ran that in the console, it'll tell you the result. In a sense, R is basically a super complex calculator. Now we're going to run several other lines. We're going to assign some variables. X is going to receive the value of 1, Y is going to receive the value of 2, and then Z is going to be the sum of both of those variables. Now, if you look at this code, you'll notice something interesting. I'm doing assignment with an arrow symbol here, but I'm also doing it with an equal symbol. What's the difference? Well, if it's going to bend your mind a little bit, we can actually do an arrow assignment to the right as well. In this case, we'd actually have to switch which side 2 and Y are on, but that will also work as well. There are multiple ways to assign values in R. All of these are valid. Some of them are more conventional or best practices, and the one that is the best practice is just to stick with the arrow symbol. But if you come from a more software-oriented background versus academia, you might just want to stick with equal sign. It honestly does not matter. Just pick one and stick with it. I usually just stick with the arrow symbol because the hotkey is Alt minus, and I'm just used to doing that at this point, and so that's fine. So now let's just say we have all this code in this code chunk we want to run, and you don't want to knit the whole document. You don't want to take up that time. You just want to run everything in this code chunk. To do that, it's not Control-Enter. That's a line. We're going to do Control-Shift-Enter and execute the whole chunk. So 7 appears, the string was printed, and all of these variables were assigned. You can see all that exists up here. If I wanted to clean out the global environment and say, okay, I don't want anything assigned to anything, I want to start fresh, I can do the broom handle here. It'll ask me if I want to do that. Yes, I just want to clean out everything. There is nothing assigned now. X is not equal to anything. I can type X in here. X is not found. So now I can just run the whole code chunk all over again. Control-Shift-Enter, and now all that stuff now exists in the global environment. All right, now we're going to get into data types. So in contrast to other programming languages like C and Java, in R, variables are not declared as a specific type of data. You don't have to say variable int and then set it to equal to something. The variables are assigned to R objects, and the data type of the R object becomes the data type of the variable. And there are a lot of different types of R objects, but the most frequently used ones are vectors, lists, matrices, arrays, factors, and data frames. A little bit about each. Vectors, everything's a vector. If you just assign a value to a vector, it's a vector of 1. Lists are lists of other vectors, and each of those vectors could be its own data type. If I have a vector of a bunch of different words, I can't put a number in there, and it has to be all the same type. Lists can contain multiple vectors of differing lengths that can be different types, which becomes what a data frame is, which is basically a list of vectors that can all be different types. So you have a tabular data set. Think of like Microsoft Excel, a table like that of data. Matrices are typically and commonly used in base R. I'm not going to get into the specifics of tidyverse versus base R. That's something that you'll get more experience with. We're going to cover just some of the basic functionality of the language. Arrays, I've never really used arrays in this language, and factors are basically like categorical variables. It's something unique that I've seen in R versus other languages, where you have code, and you have data, and you take that data and you say, this is categorical. It's not a string, it's not a number, it's a category, but you want to treat it like a category and categorize it and do operations and plots with a category versus specific counts of a string occurrence. So that string, you can actually make it into a factor, and that factor means that it is now treated as a categorical variable versus a string. This comes in very handy when you're dealing with plots later on. But let's go over these data types in detail. So first, a vector. A vector is a value assigned to a variable, or a single value assigned to a variable. So in this case, we already did some single value vectors where we did x, y, and z. These were all single value vectors. But now we're going to do something with different types and different multiple values in a vector. So for instance, we're going to assign true to v here, and then we're going to print the class. You can see at the bottom of the code chunk, the class is logical because it's a Boolean, which is true or false. Next, we're going to have numeric, and numeric is what you would say an int or a float. Both of those are numeric. So if I run that, you can see the float is considered numeric. If I change this to just 23 and ran it, it is also numeric. Now I want to assign an integer, so that's when you actually have to put the L at the end. And now it's an integer. While you might want to do integer versus numeric, is integers take up less memory than floats do. Floating point numbers take up more memory. Complex, I've never done anything with complex numbers before, but they do exist. So you have I, and it is a complex number. So now we're going to assign true, but in double quotes, to v, and that is actually a character. So this is what you would call a string. Character vectors are strings. So now if we turn this character vector, or this character string, and convert that to raw values, it is raw. And if I actually print the output of that, you can see this is the word hello in raw values. So now let's make a vector with more than one value. That's all we've been doing so far, is making a single value inserted into the v vector. But now I'm going to add multiple values. So we do that with the C function. C is basically concatenate or combine. So when I do that, and I have three different comma-separated values, you can use either single or double quotes. It does not matter in this instance. They're both treated the same by R. So in this, I can take these three values, combine them into a single vector, and send that to the apple variable. If I run that, we now have apple up here in the environment pane. It's a character vector of 1 to 3 values. So we have the index values of 1 to 3. 1, 2, 3, red, green, yellow. Those are the three variables, or three values in the apple variable. So now I can print that vector, red, green, yellow. And now let's print the class of this apple vector. It is a character vector because the three values in it are character values, or strings. Next is lists. Lists can contain multiple elements inside it, like vectors, and even functions, or even other lists inside of them. So in this case, what we have in this list is the function call list to make a new one. And we have the first item is C, the C function, to combine, or basically a vector. The vector is the values 2, 5, and 3. That is the vector. We also have the float of 21.3, the sign function, and the Boolean true value. So that's 4 items in a list. So it's going to be a list of 4 items, but one of those items is a 3 value vector. So let's run and see what this looks like. So you can see in the double brackets here, this is actually the field of the list. Below it is the output for the list. So you can see that the first value output is the vector. the second value, or the numerical vector. The second value is the float. The third one is what happens when you say the actual name of the function. It actually defines it as a function, and it gives you some strange looking output. And then the fourth value is that Boolean true. Next up is the matrix. The matrix is that two-dimensional rectangular data set that can be made using a vector as an input to the matrix function. So in this case, we have a vector here, which is AABC, BA, 6 values, all letters, so they're all character vector. It's a character vector. And we give it the function parameters of the number of rows is 2, the number of columns is 3. So you can basically cut this in half and say this is going to go below this for a 2 by 3 matrix, and by row equals true. I don't really use matrices a lot. I typically use data frames a lot, but it is important to know this. And so when I output that, you can see that we have 2 rows, 3 columns, and it's basically like wrapping that vector around itself. So next we have arrays. Arrays I don't use too often in R, but it is a common data structure used in all programming languages pretty much. So we're going to assign an array of a character vector with the dimensions 3, 3, and 2. So one very important thing to know about vectors is if you stack vectors together either in data frames, or you say you want, in this case we have an array using a vector of 2 values here, green and yellow. If you set its dimensions to 3, R does something called recycling, where it'll restart the vector, and say you need 3 values, but you only have a vector of 2 values, green and yellow, well then it'll start over at the beginning and print green again. So this is what vectors do. If you have a vector that's too short, it'll start repeating its values. If this is behavior that you do not want, you need to pay attention to the length of your vectors and what you're doing with them. So we're going to assign this array to the value of A and print it out. And you can see that we get repeats. We have green, yellow, and then it starts over at green. But then it repeats again. So it's green, yellow, green, yellow, green, yellow, and you can see it repeats each of the 2 values in a 3 by 3 matrix. That's what this dim function is saying, or this dim parameter. It's saying that the dimensions of this array are equal to the 3 values in this vector, which is a numerical vector, of I want a 3 by 3 array using 2 values. The 2 values are this character vector. And so it basically does the same thing as a matrix in this instance, where it wraps around and around, repeating that vector, green, yellow, green, yellow, green, yellow, green, green, yellow. And we actually have 2 of these arrays. So I mentioned factors earlier. Factors are those categorical variables, and we are going to say apple colors here are equal to green, yellow, red, green. We have a bunch of different variables or pieces of data in this array, or this vector. So we're going to take this vector of multiple values, and we're going to assign it to apple colors. So now we have repeats in here, but we want to treat this as categorical versus as multiple strings. So what we're going to do is we're going to take this variable that's holding this vector, and we're going to put it through the factor function. So this is going to take these strings and make them into factors and group them categorically. And we're going to assign that to factor apple. So now let's print that. And you can see it prints out all of those values, but we also have, here are the levels. So in this case, we can actually see that if you wanted to have a long list of a variety of different values, and you wanted to see like what the levels are, in which case, what are the unique factor levels, we can see that there's only 3 of them. You could also throw this into a different function and actually count up how many unique instances of each of these categories, and that is also possible. So you might want to do this if you have a value of male or female in a data set. You can actually do that categorically on those 2 string values. We also want to print the number of levels with the nLevels function, and you can see that the levels are 3. And finally, one of the most commonly used data structures is data frames. Data frames are used in Python as well with the pandas package, and they can even interchange between R and Python if you did Python code in here. So Python and R can actually interface very well and pass back objects from Python to R, so you can actually use both languages for your data analysis if you so chose. And data frames are created with the data.frame function call, and you can just pass in a bunch of different vectors and their variables, which it becomes the column headers. So in this case, we're going to make a data frame with the variable or the column header gender, height, weight, age, and assign those 3 values. Now with data frames, this is why data frames have also a very useful structure, is that all the columns need to have the same number of rows. So all of these variables we have here that are basically going to become column headers with each of these in each row. So male 152, 81, 42 is one row, and it's basically transposing this, but into a data frame. And if you wanted to have a missing value, or if you had, like, say, 4 fields in here, but somebody didn't have their weight recorded, then you would actually have to input an NA, or not applicable. We don't really use null in R. It's NA for a missing value, in which case then it would actually work. But if you don't have those and you only have 3 values, you need to have 3 values in every single vector for the entire data frame. This is very important if you're going to do it manually like this. Typically what you end up doing is you actually import data from a CSV, from JSON, or whatever data entry format you're importing. And what you'll need to do is actually clean that data as it's going into R, or R will say, hey, there's missing values, and you need to determine what you're going to do with that. This is all part of the data cleaning process that you'll go through with R. But in this case, we have a very simple data frame, 4 columns, 3 rows, and we're going to print this out. So let's actually run this. And so reading this, the variable BMI is going to be assigned a data frame containing these 4 columns with each of these rows. So now when we print this out, R is really interesting when it prints out data frames because it actually gives you this nice graphical output below this code chunk. So I can see that I have 4 columns here, 3 rows, and all of the data is represented here. If you have a very large data set, it'll actually give you pagination. So that means you can see other variables and more rows by clicking on buttons that'll actually page this for you in this preview. Or you could also go to BMI up here, and you can see, you have a little bit of information about it, such as these 3 columns in this data frame are number columns, or numeric, and gender is a character. If this was a factor, which we can actually make, so we can do, the function was factor. So now in the environment, we can see that gender is now a factor with 2 levels, male and female, and it actually displays this change in here. But if you want to see like the whole view of the entire data set, you don't want to deal with the pagination down here, or you want to just see it in all its glory, you can click this little button right here in the environment menu, and it'll actually open up a new window of your data set in this almost Excel-like grid view. And this is very useful if you just want to get a giant view of your data set, and that is data frames. So far we've talked a lot about data structures, vectors, data frames, and your overall data structures in a programming language and how to assign values to variables. So let's start doing something a little bit more fun that has a little bit more meat to it. It can immediately give you value when you're going to do any sort of data analysis and actually help you with your work, not just here's how to do a for loop, here's how to do an if statement. These are important concepts, but in R, sometimes it's just getting work done that's the most important thing. So on that note, what we've covered so far is a lot of base R material. Base R is the base library of the language. It is the core of the language. It is where everything starts out. Now you can develop packages and extend the language, just like how in Python you import new packages, you have other JavaScript libraries. The same concept is throughout most programming languages. And with the package system in R, there's an ecosystem of packages called the tidyverse. A single package called tidyverse, when imported, imports a group of projects, or projects, an ecosystem of these packages. And these packages all work together using what is called a tidy data format. This was created and written about in a research paper in the Journal of Statistical Software by Hadley Wickham, Chief Data Scientist of RStudio. Tidy data is a way of structuring your data to work with the tidyverse and a way of making a consistent and robust analysis. So when we use the tidyverse and the functions and packages within it, it actually lends itself to being a consistent format of performing an analysis. All the packages use consistent syntax, similar function design, and it will all work seamlessly together and be very familiar and allow you to achieve a lot of results without having quite as much of a learning curve when dealing with all these different disjointed packages by a variety of developers who all do things different ways. So let's just dive right into it. One of the main packages in the tidyverse is something called Dpylr. So when we import the tidyverse, we're going to library tidyverse, and we're going to import it, and now we have it in. We are going to start doing some actions with Dpylr. Dpylr is really great for filtering, transforming, and manipulating your data. You get data, it might be messy, it might be disjointed, it might be filled with null values or just things that need to be cleaned up and taken care of, and then you want to start performing some analysis. You want to look at your variables. You want to look at this data and say, what is this telling me? What are some questions I can make up from this data that I want to answer and provide to others? So we're going to work with this little built-in data set from the tidyverse package called MPG, which is car mileage per gallon. And we have a variety of data points in here. You can see that this is a 200 and something row data frame of several different variables in here. So the first thing we're going to do is use the pipe. So if you've done anything with the command line and with Unix or Linux, Mac OS, Bash, you might know what a pipe is. When you take one action and you take its output and then pipe that in as the input to another action. So if you're on the command line, you might grep some text and then pipe that into something like awk or whatever you might want to do. So the same sort of concept exists in R, and this is probably one of the most powerful features is the Unix-like pipe operator. And what it looks like is this. So RStudio has a keyboard shortcut to automatically insert this character, and basically what this is doing here is the filter function is going to receive its first argument, the first parameter of this function is going to be this entire data set. This entire data set, basically this tabular set of data right here, the data frame, is going to go in as the first argument of the filter function. And if we look into it, the first argument that these tidyverse functions expect is the data. And this is how it is consistently set up and really useful and consistent. So we can say, hey, use this data and then do all of your other actions for it. And it's going to work like that for pretty much most of the functions in all of the packages in the tidyverse. The first parameter is what data. That data is in the form of a data frame. When the data frame is operated on by the filter or whatever function, the output is a data frame. If we continue to pipe this data frame through these other functions, we can achieve some quite dramatic and useful results. So let's do that. So because MPG is going to be the first argument in filter, I don't even have to put it in as an argument. It's already in there by the nature of having been piped in. So what do we want to filter? I want to have only rows returned where the model of the car is equal to A4. So I can just do model is equal, double equal sign for, because it's not an assignment, it's comparison. And we're going to say the string A4. And you can see that this is a character vector, which means that it has a string. So when I run this, Control Enter, you can see that the green line executed. This means the pipe forces this to go to the next line to process as well. If you have a pipeline like this, it'll run everything in the pipeline. And now that 234 rows is now 7. So next, we're going to take all this output, this 7 output right here, and we're going to put it into the arrange function. So now the arrange function is going to be receiving the output of the filter function. The input to filter was a data frame, MPG. The output is a data frame of MPG, but only where model is equal to A4. And now that is the input to arrange. So now what we want to do is we want to use the arrange function to use a variety of sorts. The arrange function, you can think of it as, I want to sort by this column, and then by this column, and then by this column, etc. And it can go infinitum. You can just continue to sort as much as you'd like. So what we want to do here, let's use some numeric values so it's easy to see. I'm going to use Dpylr and cylinder. So we're going to see these two columns be sorted, but I'm going to list Dpylr first. So we have the first argument. The input is still the resulting MPG data frame after being filtered. And then I'm going to say sort by Dpylr first, then by cylinder. So you're going to watch these two columns change. And so now you can see that Dpylr is sorted smallest to largest, and we have two values of 1.8. Those are both 4. 2.0s, 4s, and then these continue to go to 6s. But this one is sorted first, followed by this one. It just so happens that they both coincide this way. So the arrange function can do a variety of sorts, and just like I did multiple arguments here and it can continue to go on, filter, a single filter function, can also do multiple filter criteria in a single function call. So with this way, you could easily pipe and chain all of these different commands together to just reshape all of your data in just a couple lines of code. So now I'm going to take all of this output and I'm going to pipe that into the Dpylr mutate function. The mutate function will create a new variable using other existing variable data while still retaining the old column. So I want to do something, and I want to say anything before the year 2000 is an old car. So let's do that. We're going to say that age equals, let's say year is less than, actually, let's make this old. We're going to ask a question. Is it old? And it's going to be true or false. So if the year is less than 2000, then it is an old car. So now this new variable is going to be tacked on to the end of this data frame here. So we have all this output. Every operation is executed every single time. So this is what we're currently working with. So now this is what's going to be transformed. So now when I execute this, all the way at the end here, we have old. And it's true and false, asking our question. 1999s here at the top. Yep, these are old. 2008s, these are not old. And so now we have this new piece of data. We've done a calculation, and you can make this as complex as you'd like. And you can create new data. And because these columns, or in this case, single data type vectors that make up a data frame are all, well, vectorized, you can do a single operation and it works on every single quote-unquote row. And data frames are rectangular or square shaped, so you have to have as many rows for every single vector, and every value has to be filled, even if that value is a missing value. So now we're going to use the transmute function. This is what you might want to do if, say, you want to calculate on an existing variable, but you want to transform it into something and then get rid of the old one. So say like you have a piece of data where you just have gender represented by M's and F's, or whatever other characters you might use, and you want to completely replace that with male, female, whatever else you might want to put there for a gender, and then you can do something like transmute that into actually giving those full words and then turn that into a factor, etc. You can see how all the different ways you could take this different type of analysis. So let's do something where, let's see, what can we do? Let's take drive, and instead of F, let's just make this full wheel. So before we take the output of mutate and do something with it, we actually need to pipe it. So the output of mutate is going to go pipe into transmute. And what we want to do is we want to look at, what do we have here so far? Let's run all this. And we have drive, and we want to change that to full. So let's do transmute full wheel drive is equals drive equaling F. And so this is true. So what just happened? So we transmuted and we kept the new variable, but all of the older variables, all the other ones, were discarded. So in this case, transmute says, okay, here's a variable named full wheel drive, and we're going to calculate on that, and that's what we're going to give you, but you didn't say anything about anything else. So sorry, buddy, that's all you're going to get. And in this case, what I might want to do is say, I'm not going to use transmute here. You know, there's a use case for every single one of these functions. Somebody somewhere has found it useful. But what I'm going to do is I'm going to comment this out, and I'm going to say, hey, Dpylr mutate. Once we get here, what does your output look like? Oops. What does your output look like? And I want to create a new column named drive, and I want to drop, or full wheel drive, and I want to drop this column. So I don't want this to exist anymore, but I do want my full wheel drive column. So what I can do is I can say, hey, mutate, comma, I'm going to give you another argument. Full wheel, if I could spell right today, equals drive if drive is equal to the character f. And so now what this is going to give us is a new column at the end. Yes, these are all full wheel drive, but we still have the drive column. So that's where we can do something like the select function. The select function does exactly what you might think. You're going to select some columns to keep. So in this case, I want to keep all of these columns except drive. So select can work both ways. You can either select explicitly, I want this one, and I want this one, and I want this one, and I only want those specific ones I mentioned, or you can do something like piping all of this output into select and say, hey, I want everything minus drive. So when I run this, because it's part of the pipeline now, it'll run all of that, and now the drive variable is gone, but we still have full wheel drive over here. So now we have transformed our data and through all of these different operations, and look how little code it takes to do this versus something like any of the C languages versus something maybe like JavaScript. This language is specifically geared towards vectorized data analysis and manipulating and changing data. And this is just a couple functions from one package in the tidyverse using the tidy data format. This is how powerful this language can be. So I'm going to show you one more function for Dpylr before we move on from this little section. And to give it justice, I'm going to actually just take the full MPG data set and I'm going to pipe it into the count function. This is a really useful function just to get a brief overview of your data. You want to see like, hey, how many times does this one specific value occur? Throw it into a histogram or a bar chart, whatever you want to see what it looks like. Let's do that. So first of all, let's just toss it in there. We have 234 records. If we don't specify a column, they'll just say, hey, how many rows are in this data set? But what I want to see is I want to see the count of model. So when I run that, cool. So we have all the different specific models. They're characters, but in this case, we're counting each unique character. In this case, this works. You might want to change characters to factors in one way. It can depend, but for what we have right here, this is interesting. This works. But I don't like the way this output, this n for number, yeah, okay, cool. But why is it all weirdly looking like this? Well, we can go into the count function, say, hey, sort this, and you're going to say sort equals true, because I do want it sorted. True in R can either be T or true in all caps. For shorthand, I just do T sometimes. But when I run that, now we have a sorted count, and you can easily see which things are the most frequent occurring and which are the least, which is actually A4 that we pulled out earlier. So Dpylr is incredibly useful, really concise functions, do immediately what you want, and clean, reorganize, get a good look at, and investigate your data sets. Probably one of the most, if not the most popular package in R is the ggplot2 package. ggplot is a plotting package. GG stands for Grammar of Graphics, and it's a graphical package that lets you create data visualizations with your data sets. It is used all over the world by high-level academics, PhDs, by professional journalists, I think the Chicago Tribune, the New York Times, a lot of investigative journalism that actually reports on data will use ggplot and R to actually create these complex, highly detailed, and visually appealing visualizations. So ggplot by itself, without getting super complex, is a relatively simple function. So ggplot takes some data, it says ggplot, here's the data, data is equal to whatever data set, and because the first argument is already assumed to be data, you don't even need data equals, but for the sake of understanding which arguments are going to which named parameter, we're just going to leave all this stuff in here for, even if it is verbose. But in this case, I'm saying, hey, we're going to make a ggplot with the MPG data frame, which is the full data set, the whole 234 rows we saw earlier. Geom is a layer. You can think of ggplot right here. This is going to be a blank canvas. Cool. Yeah, a blank canvas. Yeah, the MPG data set is in here, but we didn't tell it to do anything. When you use geoms, like geom point is a scatter plot or a graph with just a bunch of points on it. You give it an x and a y value. Those get crossed on here, and where they intersect, that is where the value is plotted. This is a scatter plot. And all we have here is I'm mapping the aesthetic, and the aesthetic is this x and y axis on a scatter plot chart. And then what is being x and y? These two variables from the data frame that is listed in the ggplot data. Now, one little interesting thing to note that is likely not going to change until the eventual, maybe future iteration of ggplot 3 if it ever happens, is that Hadley Wickham created this package before he discovered that pipe operator we had earlier, so we can't just pipe this into the next function. So in this case, ggplot is that one weird little, redheaded stepchild that has this plus operator to carry on to the next action. So you take each of these items and you add a plus at the end, or you can structure it differently and have a plus at the beginning and do some other weird ways of structuring this, but you have to combine these functions with the plus to add them all together. Because what these geoms do, and you can use multiple geoms on a single chart, and this is how you create these very robust visualizations, is you're basically adding a layer of paint over your chart. You have a blank canvas, you're adding a layer of paint. You can add another geom using additional criteria, colors, graphics, variables, and keep layering on that paint until you get a really pretty and very visually interesting and communicative visualization. Let's look at what this does. That's enough talking. Data equals MPG, dispol, and highway, x and y. Let's run it. When I run that, we get this is the default plot. You just said x and y. Everything else is defaulted. This is just a ggplot, a very simple ggplot. And we could see, oh, wow, actually, this is actually a kind of very interesting distribution here. We have a downward linear regression. I mean, there's no regression line here, but you can see a downward trend. So we could plot a regression line on this. But we also have these outliers right here. And so we might ask questions like, hey, why is the highway so high for these guys, but they have, high level numbers here? I'm not a car guy, so I don't really know what these variables mean when they're shortened like this. But in any case, interesting data. So we could also add additional criteria to this. So we're going to take the exact same plot, but we're going to add a new variable. Instead of x and y, hey, the color of the points are going to be differentiated by class. So now let's see what happens when we do that. So now we have class. Each of these different classes, basically a factor or a category, a categorical variable of the data, now changes the color. The points haven't changed. Their location has not changed because x and y has not changed, but their color has, and now we can see groupings and where these might land. So just with these three little variable assignments, we're able to actually get a good deep look at our data and try and understand something about it and ask really important and pertinent questions that we can dive and delve deeper on. So let's do something even cooler. One of my favorite things to do, we have MPG, we're doing x and y, but what's this facet wrap stuff and what's all this? Let's run that. So facet wrap, we're wrapping the facet by class. So facet, you can think of like a diamond. A diamond has multiple facets, different faces, and it looks at the inside of the diamond in a different way through each face. In this case, we're faceting by class. So each class has its own chart. And you can see the scale here for each of these graphs is still the same, 0 to 7, and the y-axis is also the same, 0 to 40 or whatever up here, but each class is on its own separate chart, all lined up next to each other so we can see the distribution of each class. And then we're wrapping, so basically going left to right, top to bottom, and we're only wrapping for 2 rows. That is what these arguments do. But here's one different change. Instead of facet wrap and wrapping around, we're going to do a grid. And we're going to do a grid by the drive and cylinder variables. Ignore the tilde. It's not a little bit out of the scope for this, but that's just the syntax we use for here. Long story. Let's run this. Facet grid. Ah, interesting. So drive, we have the numbers on the x-axis, and cylinder we have over here. Or I guess this is drive and this is cylinder. So in any case, we have these two facets over here. So we have X and Y, highway and dispo. Those have not changed still. But now we're adding facets on the top and on the right by these two variables. You can begin to see how you can chop, slice, and dice this data and how you're visualizing it to really see it in new lights and in new situations to ask those questions that pop up when that doesn't look right, or that's interesting, why is that way? And then you can really start to pinpoint these critical questions, especially if you have business use cases and you're trying to find answers as how can we as a business make more money? Well, what does our clients buy? What are their spending habits? What do they buy more often? When do they buy that more often? Like, you can see how all these data points work together, and then you can try and look at that in using these tools and try and find out when is a good time, what is a good product, when is the right time to market this, and all these types of things that can be answered by this data. So now we're going to do another geom point right here. Go back to classic. So this is what we started with, plain old one. So now we're going to add a second layer of paint. We were still doing only one geom point, but now we're going to do another one, geom smooth. We're going to use the exact same variables, X and Y, highway and dispo, and in the exact same data set, but now we're adding another layer of paint. What's that going to look like? So now we have this. So what geom smooth is doing is it is adding a line, and it's like a curved regression line where it's saying, hey, how close can I be to every single point as I run through it? And it's trying to be as close to every single point and find the minimal amount of distance. I'm probably explaining this very badly, and then the gray area is like the margin of error for where that line is. But in any case, we added a new layer of paint to this, and it further and deepens our understanding of what this data might look like. It adds another visual and a way of interpreting this. So now let's just add geom smooth without actually using the variables, just a plain geom smooth. But we also changed some stuff up here. So now we have ggplot, data, the mapping is X and Y up here, geom point is just color equals class, and then a empty geom smooth. What does this look like? Interesting. So now we have color by class, we have geom smooth, we have colors, we have a little bit more visual information. We can see our cluster, we can see our geom smooth line. And finally, let's just do a very simple one we haven't seen yet. Let's just do a bar. And we're going to do it with the diamonds data set. This one comes with ggplot too. And we can see, interesting, we have the count and the cut of diamonds, and ideal is the most commonly used, or the common count. So you can see just by these very simple examples, very super simple examples, what you can actually create with these very simple functions. I mean, this is like 3 lines of code, and look what I'm able to get as output just with a tabular data set. You could just write a bunch of data into an Excel spreadsheet or a CSV, throw that into R, and just start plotting, and then you can actually see and visualize your data like this. And the more layers that you add, the more paint you add to this canvas, the more you might actually be able to glean from your data set and be able to understand and ask those questions that you really need to be asking. So next we're going to look at a little bit more of those questions, exploratory data analysis, looking at your data, asking those questions, and just looking at it. All right, we've taken a look at how to filter our data, mess with it, clean it, and then how to do a little bit of visualization with that data. So now we're going to do a little bit of exploratory data analysis, or EDA. This is a very common term, and it's basically most of the job. It's really you're just looking at the data set, finding clues, looking for weird abnormalities, outliers, cleaning it, shaping it, visualizing it, and constantly iterating in those workflows to find and dredge up those interesting questions. So we're going to take the diamonds data set and we're going to do something with it today. So this looks like a very interesting thing we haven't done yet. So if you remember from the beginning, the arrow sign is the assignment operator. So it's saying it's basically smaller is equal to diamonds, but we have a pipe here. So how does this work? So this is one of those weird little quirks of R that people sometimes get a little tripped up about, is that they think that diamonds is being assigned here and then something's happening with this, or what happens here? So the way I like to read this, and I read it out loud like this so that you can understand how this actually works. The variable smaller receives the value of the output of diamonds being filtered where caret is less than 3. So if the caret is less than 3, then those records in diamonds where caret is less than 3 are then assigned to smaller, the variable. So now smaller is a data frame from diamonds as a subset where only caret less than 3 is assigned to this. So now let's run this and see what it looks like. So there's no output because we actually assigned it. So up here in the environment pane, if you're using RStudio, and I prefer to use RStudio, we have almost 54,000 observations, or 54,000-ish rows of data of 10 variables. That means we have almost 54,000 rows and 10 columns. If we just do a little preview here by clicking this button, we can see some data types, we can see some sample values. We could click on the little button right here to preview it and look at it. I'm not going to do that just because I don't feel a need to. But that's still a very good sized data set. So that's a lot of diamonds that have less than 3 carats. So now we have this in the environment. So it's declared, it exists. We can now use this in other things. That variable now holds data. So in this ggplot we're going to make here, data is equal to smaller. So the new data frame we made that was been filtered, where the mapping of the aesthetic is x equals caret. Okay, so we're going to do a plot where the x-axis is equal to the variable of caret, but there's no y-axis. Why is that? Because we're doing a histogram. A histogram is not like a bar chart. A histogram is a distribution. So we're going to do a histogram where the bin width is 0.1. So what does this mean? A bin width is just saying, hey, if you fall in between 0.1 and 0.2 or 3, you're going to fall into this bin, and it's going to increment by 0.1. And this is a good way of catching if you have a lot of small values. So if you have less than 3 carats and you use decimals like 2.8, 1.4, like we saw maybe earlier, then this is going to be a good way of visualizing a good distribution. So let's just look at what this looks like. So if we run that, interesting. So we have a lot of distribution, we have a lot of values in this distribution that have a very small carat. And so very few of them actually have 3 carat. So this is interesting. So now let's do something where we change the bin width. This is also just a little bit of an aside for statistics. It is very good practice to try and look at a variety of bin widths of your histograms when you're actually plotting these, just to see how the data looks under different bin widths and distributions. So let's do 0.5 and we run it. Oh, interesting. You see how it gets all big and blocky like this and gives you less detail? This is why you might want to do, okay, that's a little too much, so let's bring it down to 3. Take a look at that. Oh, that's interesting. And this, we can begin to look at this and see it in a new light. So we're going to go back to MPG here. We're going to say data is MPG. Ooh, new geom. Instead of geom histogram, we're going to use geom box plot. Box plots are an incredibly useful chart. They tell you so much information. We're going to map the aesthetic of x-axis equals, okay, what's all this? Reorder the class, highway, and fun equals median. Interesting. I wonder what all this does. And then y equals highway. Okay, so let's look at this. Let's just run this. Interesting. So we have a box plot here. And the box plot is a really interesting chart to use because all these dots, these are outliers that don't fit in. And the box plot, by default, this line in the middle is the median, or I forget actually if it's the median or the mean, but these lines on the tops and the bottoms of the boxes are the inner quartile range. So we have like the middle 50% of your data set, the median value of that, or in this case of the variable, and then the whiskers here are actually the dregs of the data set, and then all of these are the outliers. And so you can see the distribution as you go up here. So the highway, mileage on the highway goes up over here as we get up into pickup, SUV, minivan. So based on these categorical variables, we can see, ooh, this goes up. And this is what reorder is doing. We're reordering by class, by the highway, and median. So in this case, it's actually reordering all of these so we can see like the trend upwards. So we can just see like, okay, which one is the highest? And this is how it actually reorders. And we can actually get a lot of really good, juicy information out of this box plot. So now we're going to do something else interesting. I'm going to say, ooh, diamonds, this is the diamonds data set, pipe that into the count function. You saw me earlier where I said Dpylr : : When you do this, this is just saying, instead, if you've ever used Python code or you've seen Python code where it says from this package, import this function, It's like that. So it's like you don't have to import the entire package. Like if I have a very simple script and I don't want to import an entire R package, the entire Dpylr package with all of its 50, 100, whatever plus functions, I only need one function, count or filter or whatever. I can just do double colon. It'll say, hey, from that package, grab this one function. And that way I can just grab what I need and I don't have to import the entire thing. And so if you declare it, like I said, library on tidyverse earlier, tidyverse will call Dpylr, but it's basically like saying library Dpylr and then declaring that package. Oh, I spelled it wrong. But anyways, so Dpylr count. We're going to pipe diamonds into count. We're going to count by color and then cut. So, two variables this time. What does that look like by itself? I can just select this instead of the other pipe here, and I can run selectively that code. Ooh, okay. So we get color by cut, and then we can see, okay, ooh, you see what's doing here? So each color gets its own representation for each cut. So you're basically multiplying this across. So for all the unique values for cut, times all the unique values for color, and then the count of all of those. But, ooh, I don't like that. I want to, comma, sort equals true, and let's run that. There we go. So we can see that the color G and the cut ideal is the most frequently occurring value in the diamonds dataset. That's really cool. All right, so let's take all of this output right here. The sort's not going to matter when we throw it into the ggplot. So we're just going to take all of this, and we're going to say map the aesthetic X to color. So these categorical characters here. This is an... Ooh, see, it says order. I wonder if that's a factor or not. So let's see. X is going to be equal to color. Y is going to be equal to cut. And then we're going to also add a geom tile. What does that look like? Where the aesthetic is a fill equals number. Okay, interesting. You might be able to infer what this is. Well, let's see. I spelled diamonds wrong somewhere, didn't I? Oh, I just selected it wrong. Let's just do this right there. Interesting. It's basically a heat map. So we could say, okay, we don't need to have a number scale for like a scatter plot because it's two columns of categorical variables. These aren't sorted by a number. These are colors. So it's not like it's not A, B, C, D, E. It's a color. So it doesn't really matter the order. Here, ideal could be sorted, but in the end, it doesn't matter. And the numbers, that count is just the color and the intensity of that color on this heat map. So this way we can actually order it and see, interesting. All these different colors, we can see that right here. This is the lightest. So G and ideal, that's the highest value. The darker values, J and fair, these are the least likely to occur. And so this is a very interesting geom tile. So all these examples have used these curated data sets that come with these R packages. Diamonds comes from the ggplot package. MPG, I don't know exactly which package that comes from, but it might be ggplot as well. But what do you care about? You care about your data. If you're doing something with R, you're likely trying to do something with your data. Like, I want to look at my own data, make my own analysis. I want to do these cool plots, but with my stuff, not this built-in stuff, because that's not interesting. One of my first projects, I have like a side business and on Etsy, and I just exported all my Etsy sales data into a CSV, threw it into R, and started making some plots with it. And so you can do the exact same type of thing, where you find whatever data that you want. You can just collect data on yourself if you wanted to, wear a Fitbit, get your Fitbit data, and then put it into some plots. So that's what we're going to look into next, is how to import your own data into R. So R is geared for data science. RStudio is an IDE geared for R. And that means that it makes your life as a data analyst or somebody working with data all the easier. So let's say I have data. I need to get data into RStudio so I can do R code on it. And I need to analyze this, visualize this. How do I get the data into R? So it's really, really easy. If you just have a CSV, say like a lot of your data comes in as a CSV, this is a very simple data format, very easy to parse and use. But if you have JSON, if you have a SQL database connection, if you have feather files, all of these things, R can handle so many different formats and different kinds of data. It's mind-boggling the amount of stuff that R has. It has the capability to deal with. And not to mention, if it doesn't have that capability, people develop packages to make it possible. But we're just going to deal with a simple CSV, something super simple. So I just took one of the data sets, I think it might have been diamonds, and I just saved it as a CSV file. So I have it right here in my files. So you can see, like in my files viewer over here, there's data CSV. It's 2.3 megabytes of information. I can click on this file right here. Interesting, I can view it and I can import it. Ooh, well, let's view it first. What am I importing? And it's large, so it's gonna be a slow preview. Okay, let's see what it is. Okay, it's it is the Diamonds dataset, and it's got just, it's just text. It's a lot of CSV values, comma separated values. A lot of them, almost 54,000 of them. Great, that's a lot of data. So now I viewed it, I know I want this in here. How do I get it in here? I can click import, and this works with Excel. There are Excel packages. Side note, Excel, all the .xlsx files, that X at the end, and basically all of the Microsoft Office file formats that end with an X means that they are now considered XML documents, basically, which is why Pandoc can actually convert to Microsoft Word and PowerPoint. It makes these documents a lot easier to parse, which means you can actually get your data out of a proprietary format in Excel into other things like R. So in any case, importing this way, we can read CSV, just clicking import, it brings me to this window. It already has the file pathway, it gives me a preview. I can actually do some sorting in here. I can actually change the data types if I wanted to on these, if I wanted. I can actually have some other options, and it even previews the code. It wrote the code for me to just get my data in here. So this is awesome. I'm just gonna click import. I don't even need to change anything. Only because, this is actually a curated data set. But if it was your data set and you want to do a little bit of, cursory analysis, a little bit of looking at it in this way, you could. But I'm just going to import it. Okay, so now it's in here. It's in the viewer. There's some stuff that's spit out into the console. Interesting. It has all these columns. Caret is equal to a double, a character, double. So basically, these are the data types of those columns. And then data right here. Ooh, so all of that visualized data that we saw in here is all here now. So now if I go back into here, into our actual file, I can actually say, hey, data. Oh, and then the IntelliSense tells me, yes, that data object does exist now. It's a little table in here. That lets me know that this is a data set. So I can click in there, run that, and then we get our output. This is the Diamonds data set. So that's a very quick way of getting a tabular data set into R. It's already in here, just like we were dealing with everything else. So from this point on, everything we've already done, you can now do on your data. You got it into R, you know how to filter it, you know how to sort it, you know how to plot it. And if you don't, there's just a couple quick Google searches, and ggplot, super easy to get started. ggplot, put your data in there. Mapping equals aesthetics, and the aesthetics are your X and Y. Make a genome point, you're off to the races. That's all you need to do just to get started. So what are some other ways of getting some data into here? Well, if you just have a very small data set or something where you want it to look familiar, you want it to look somewhat normal and organized to you, there is something called tribbles. Tribbles are a part of a package in the tidyverse where you actually use a tribble is a row-wise tibble. A tibble, without the R here, a tibble is like a data frame, but with a little bit of extra features and spice, I guess. A tribble is just a row-wise tibble. So when you can see our data sets, when they're displaying like this, here are the column headers, here's the variables down here. But when we actually have, when we assign to data frame earlier, I think it was right here, yeah. When we assigned to data frames, you saw that it was column headers on the left, and then variables going, the actual values, the rows going horizontally this way. It's basically like transposing this 90 degrees over, and it's a much easier way of actually reading your data. So in this way, I can just say, here's my header for pregnant, and in each row has that entire observation. So you have a variable vertically and an observation, a complete observation horizontally. So if you're pregnant, yes, you're obviously not a male because males don't get pregnant, and female 10. If you're pregnant and no, well, yes, all 20 males would be no, and then 12 females were no. So in this case, you could easily just lay this out, say, hey, make a tribble out of all of this, and then assign that tribble to the value preg. So we can just run that. Cool, we now have that. We have two observations of three variables. The three variables are pregnant, male, female. The two observations are yes and no, and then the accounts for those results. I can run that set, preg, and there's the output, and it is assigned exactly how it looked here. So it looks familiar, it looks easy to assign, and it's all just formatted this way. But it is a lot of extra typing to do. And we also have these little tilde characters for each column header. Everything's basically a CSV. It's comma-separated values except the last one. It could be a lot to write, which is why we're going to come into some of the cool packages I'm going to showcase here in a minute. The party winners, I like to call them, because there's just some really cool functionality with just, you don't have to do anything. It's just by itself. It's just amazing tools. And one of them makes tribbles a hell of a lot easier to do. So let's take a look at those next. So I'm going to show you a couple packages today. These are ones I just want to call party winners. They're just amazing packages for what they do. And these are just 3 simple packages in the entire ecosystem of R. There are so many packages for so many different things. You have PhDs writing packages to do highly complex analysis in their narrow scoped fields. You have people writing general purpose tools, and just the general tooling of making the R language better, not necessarily the actual analysis of data. It is just an amazing ecosystem of developers creating a robust and super flexible and powerful language. I even made a package myself dealing with conversion of different characters through Unicode for linguistics, and it's on my GitHub if you care. But in any case, the 3 packages I'm going to cover are Dpylr. I can't pronounce this, it's French, I'm not going to even bother, I'll just butcher it. And then Ray Shader. So I mentioned earlier that tribbles can be a lot to type, and they can be. So there's this package called Dpylr that just makes copy pasta, if you know that term, pasting data super easy just to get it into R. If you don't want to have to import a file, you just want to copy and paste something and get it done, then Dpylr is for you. Dpylr, when you actually load this library or install it, it comes into the RStudio add-ins. You can see Dpylr right here and all this stuff right there. Let's look at what this does. So I have the data set open. I don't want this view. I actually want the file view. So I open up the Diamonds dataset, CSV that I have here, view file. Yes, it's large, I know. Open that up. Okay, here's our CSV, just a bunch of raw text values. I'm just going to select all, copy it, and now I'm not just going to paste in here. I'm going to go to add-ins, Dpylr, tribble, paste as tribble. So it will take a little bit while to load because that is a lot of data just to spit out into an actual R document. But you can see that what it did right here is it made all of my column headers for me, everything separated by commas. It actually has some syntax highlighting. The tribble function call is being called. All I have to do up here is say, hey, here's my data variable, and I'm going to give it the assignment of all of this tribble information. That's all I have to do. Now I have my data in a variable and I am good to go. And one really cool thing about Dpylr is that you can also just do this with HTML tables, I think. You go to a web page, you see an HTML table, you copy that, you can paste that in as a tribble. It'll actually recognize that, and it just works off of your clipboard. So next I'm going to cover this French package. Again, I don't want to butcher the name, but this is amazing. I mentioned earlier that you just do a very simple geom point scatter plot, you're off to the races with ggplot. I remember walking into R and thinking like, whoa, this is some interesting syntax here. How do I get good at ggplot? That's the whole point, isn't it? Like I want to make really cool looking graphics that tell a good data story. But I have to do a lot of Googling just to figure out how to get something simple yet elegant created. And ain't nobody got time for that. So what's a simple way if you can just create something good and then maybe analyze the code after the fact when you have some time to see how it's doing what it's doing? Well, that's where this package is really, really useful. It's also in the add-ins bar like Dpylr, but right under here we have ggplot2 builder. So when I go into here, there's a bunch of built-in datasets. First of all, I can choose a data frame of something I already have in my environment. So I can just create a variable holding data and then make something with it. Or if you have, sometimes if you don't have anything in the environment, if you actually have a loaded datasets like all the diamonds, MPG, the iris dataset, sometimes those will just appear in here and you can play around with those built-in curated sets. But in any case, we have data. So I'm going to pick data. Okay, so we have 10 variables. I can change some things about it. Again, it's curated. I don't need to, but I could change things to, characters, factors, dates, etc. I could coerce those different things, but we're just going to go in and mess with it. All right, so we got our variables in here. We have, what's all this? Oh, interesting. Plots, okay, some empty boxes. Let's start playing around. So I have cut under X, color under Y. That doesn't do anything interesting. Okay, cool. Let's drag that out of there. Let's put price in Y. Interesting. Ooh, wow, that's interesting. And it just immediately changes the plot type. So let's take that one out. I think these ones are the actual categorical, and these are the numerical. So this will give us more data. Now we got a point. Ooh, that's a very interesting distribution here. And so we can start drawing some conclusions from this. Like most of these fall on these specific points and then scatter out away from those points. And these are more of the outliers. But it also does have a more of a linear trend going, positively up here in price as the caret increases. Interesting. So this is a way you could just play around with your variables really quickly, see what it's going to output and say, oh, wait, I want this one. I like this plot. I want to actually put this in my report, write up some analysis about it. But we also have all of these options down here. Labels and title. I can give this plot a title. Here's my title. I can give it a subtitle, a view of diamonds. Caption. Hello, caption. I don't know, I'm going to run out of stuff here, but X is caret, Y is price. Cool. Plot options. Oh, interesting. Add a smooth line. Yeah, why not? And then let's do a color. I don't like that color, so I'm just going to do this one. And theme, minimal. Okay, that's fine. Legend. I like my legends on top. Go to data. Yeah, all this looks good. I don't want to filter out anything at this point. Export. Oh, okay, cool. I could save this to an exact picture. I could save it to a PowerPoint, or I could just grab the code itself. I could, if I have my cursor right here, I can just insert this directly into my script. Here's all the code. Insert it. Now it's in there. It's already done. That whole plot is now written for me. I didn't have to do anything other than click some buttons, drag some fields. I could copy it to the clipboard and paste it. But in this case, what you can do is you can change this stuff up. So now I want to change the plot. I want to change the color to this. I want to remove the size of that. I don't want a smooth line anymore. I want to change the depth to that. I don't know, some random stuff. And then I can just do, after it finishes loading that, insert this into the script. So I was clicked a little bit too fast because this is a very large data set to calculate in this manner. But when you click insert this code into your script, you can basically create a bunch of different plots, mess around with your data points a little bit, switch some things around, click insert into your script, and then you just have these plots and all their minute changes just dropped in here for you to mess around with later. So this way you could easily, quickly build something, get it done, put it in there, analyze it later, figure out how it works, but just get something done and ready. This next one is not something that I deal with. Like, this is way beyond the scope of any sort of data sets that I deal with. I just think it is absolutely the coolest thing to just take a couple lines of code and do something really amazing with this. The talk that the creator of this package made on this package is simply incredible with the work that he put in on this. But this package, Ray Shader, if you know anything about like ray shading and game creation, game development, or low-level systems programming in C languages, you might have an idea of what this might do. But if I run this code, and I'm going to cut some clips because it might take a little while to render, but there's some really cool output from using the Ray Shader package. So the output of this little code, there's just these couple lines of code here, is this rasterized image of some actual physical terrain using a matrix observation and a file that is actually imported from the web. So we just download a file into a temporary file, rasterize it, put some stuff, I don't even know what half this stuff does. It just makes a really cool map, and it actually deals with terrain. I thought this was really cool, and the next one is really going to blow your socks off. And so the output of all that second part of the code is this rasterized image of a 3D data visualization. We can actually see the X and Y axis, but we also have the third dimension of height. And you can see the legend over here that the height is to deal with the count. And you can see the different colors as well. You can create these really cool and interactive plots using the Ray Shader package. When I found this package out and I saw the talks on this, I thought that this was just the coolest thing ever. And we also grabbed some snapshots from when the code was ran, so you can actually see these are the types of visualizations that are produced. And again, with the right know-how and minimal code, this is not a lot of lines of code to produce these very rich data visualizations that tell really interesting stories about the data and the way it was collected and how it was interpreted and cleaned. So I hope by now you can see the power and just the sheer amount of awesomeness that R is. I could go over like this is how you add items together, a plus operator, minus operator, how to do Boolean comparison, this and this or that. A lot of those are just the fundamental programming concepts, ubiquitous across all languages for the most part. And that's not really where R shines. R shines in actually doing data analysis. Get your data in, do something with it, clean it, shape it, plot it, write it up, and talk about it. And this is where R is just a magnificent language. It's a great intermediary. You can interface with a variety of languages. Is R too slow on this function? You can write that function in C++ with its interface to R and have that function execute as a compiled binary really fast, return the result to R, and let R continue on its way while taking advantage of the speed of a lower level systems language. You can use code chunks in these R Markdown documents that are SQL code, Bash, R, Stan, Python, Juliet, whatever you want. There are dozens of supported language engines in R Markdown, and then R Markdown itself can render to a variety of formats through Pandoc. You can have custom LaTeX templates. You can have basically custom anything, your own workflow, your package development, your actual document templates. You can create whatever you want in R, and it's not even that hard to do. I've done a little bit of development in R and actually more on the actual development side versus the actual analytics side. And I've done both sides, and it is a great language. It does have its weird quirks. It's an old language. It has a lot of baggage from its past. But if you stick with the tidyverse, you understand where it falls short in some areas, where to pick up the slack with another language or tool, the right tool for the right job, and put things together in the right way. And it can be an absolute amazing tool in your toolbox. You don't have to be a PhD data scientist working for a large Fortune 500 company earning multiple six figures to actually use R and use it well and actually get some value out of it. Honestly, when I started using it, I was just a lowly analyst in my job. I went from Excel to using R to make some nice looking documents and giving some basic summary statistics. Before I really got started, that's all I was doing. And you know what? It was great. It produced really great looking documents. I could automate a lot of my workflow with R scripts. And it was just a great tool just to get into data engineering, data science, and better work as an analyst. So I hopefully this talk has inspired you to look into R a little bit more. It's even if you use it as just an overblown and super powerful calculator, it is just a really great language. It's my favorite language, and there's always more to learn with it. And hopefully this was an interesting talk. You stuck around and made it this far. And yeah, I hope you will let me know how you like the language, if you've done with it. I would always love to hear what people are doing with R. And on that note, a big thank you to Brad Traversy for letting me, put this video up on his channel and giving me this opportunity to, gush about my favorite programming language and just the whole sphere of academia, data science, and dealing with this type of programming. There's always more to learn, but it is my favorite language, and I'm happy that you guys got to listen to me gush about it for a little while. So I will let you all go. Thank you so much for watching, and I'll catch you in the next one.